So, hi, I'm Marcello Laurenti, PhD student, first year of the University of Rome La Sapienza, and I'm here today to present you this preliminary work of an unpublished work about the determination of strain stress curves and related material properties through genetic artificial intelligence. Now, a little bit of background to make you better understand the motivation of this study. Normally, you well know that to characterize the static mechanical responses of a material, for example, of a austenitic steel, you have to test it by using mechanical tensile stress. So basically, you anchor your specimen into a tensile stress machine, you stretch it until you reach failure, and you are left with those nice tensile stress curve. Now, after you have gathered enough data, you can try to generalize the material mechanical response, for example, by using Johnson and Cook or similar model. For example, here you can use that model to generalize the plastic deformation of the steel. But until now, this kind of generalization is not possible for different material composition. So every time you discover or you are testing a new composition for a steel or for an alloy in general, you must repeat the procedure all over. So the objective of this study is to develop a deep AI model to make this connection. This assumption was based on a previous study, our previous study. If you're interested, this is the title of the study, and it should be published in the next issue of Engineering Application of Artificial Intelligence. So our goal here is to correlate the composition of an alloy, the testing parameters of the deformation, and obviously the strain path. And after we will be left with with a generalization model capable of predicting the mechanical response of of an alloy. And this is very important because it allows us to make an active learning procedure to optimize maybe the composition of an alloy, given maybe our desired properties of that material. So how we are planning and how we have conducted this study by using this kind of architecture. So we have decided to use different family of architecture. The first one is an encoder-decoder. They are easy to train and they give good accuracy. This kind of architecture are the one used in the previous study. Temporal convoluted network family. They are very easy to train thanks to the convolutional layers, but they have a serial limitation because the sequence length must be fixed, and that could be a problem if you are planning to generalize the behavior of the material. And after the last one, the N-bits family. It's very similar to ResNet, but here actually doesn't use a convolutional network layer, but a fully connected layer. So it's faster to train, and the peculiarity here is you can use here user-defined functions. So you can force this model to behave like a physically informed model. So I mean, you can force him to have your desired physical behavior. So the choice of the architecture is only half of the work, because the other half is the optimization of the hyperparameters of the architecture. And to do that, there are several ways to do such an optimization. The most naive one is the grid search, but in our case, it's unfeasible because we have a very large search space. So the whole time to actually do this kind of space searching will be practically infinite. The Bayesian optimization is normally the best way to go to do this kind of optimization. But here, as I said, the optimization space is too big, and we have too many categorical distribution. So this optimization could and will collapse in a random search, so we cannot use it. We have decided to use the state-of-the-art optimization algorithm called the genetic optimization algorithm. They are bio-inspired as per definition, and they are very effective in a very wide plethora of application. So what is a genetic algorithm? In our case, a genetic algorithm is applied by dividing at first our architecture in different blocks. Each blocks will represent a gene, and each ensemble of genes will represent a chromosome, and each chromosome will compose the genome of an individual. I'm talking about individuals because this genetic algorithm is a population-based approach. So in our optimization procedure, we have created an environment with n number of individuals, each one with their own genome. And each generation, only the fittest individuals will survive and will pass their winning genes to the next generation. So by doing that, the population will be more fit, and we will achieve an optimization of the performance of the model. Here, the fitting, the fitting of the individuals is evaluated by using this loss function, the soft DTW. The soft DTW is a loss function very similar that performs something very similar to the Euclidean distance. So it's very similar to the mean absolute error and the mean square error, but it's quite different because it takes into account also the temporal correlation or the spatial correlation of the input. So it's very useful in our case study. And we plan to go further and to extend the capabilities of the genetic algorithm by using a species-based environment. So we planned to introduce an environment with different species. So we have not planned to use the whole triangle, but only this section. So individuals that were of a class, an order, a family, a genus, and species. Some species could mate with each other, some not, like in nature. And why we establish such an environment? Because in this way, a new architecture would be created, and this architecture will be highly specialized in the task. And the new created architecture could have a structure never seen because they are not engineered by a human, but by an algorithm. So as for the methodology, we have developed a general framework where a local controller is responsible for the genetic optimization, and it push all the configuration on a SQL server. And the configuration are pulled by workers on an HPC cluster. These configurations allow for perfect scalability. The only bottleneck here is on the SQL server, but we have run maybe more than 100 workers in parallel. So, I mean, that's not an issue. After this optimization procedure, after n times, which n is represented the generation, we have reached convergence, and we query the best model, we evaluate on unseen data, and after that we evaluate on real tensile strength tests. Now, for the preliminary results, I want to stress that this is really a preliminary results. We've used a very small section of our data base just to prove this concept, and we achieved actually very good results. These are results relative to the 316 L stainless steel. And we trained on a small domain, and we validated on a very distant domains. And you can see here the prediction are quite good, are quite in accordance with ground truth. So the model was able to generalize. In this case, the genetic algorithm was applied to the encoder-decoder family. In conclusion, the library right now is fully completed, integrated with PyTorch with a HPC support and cloud. You can see here a preview of the library that's almost a software. And the datasets, we have built a dataset with 10 and more different stainless steel and of course their strain stress curves. We have reached very good results, preliminary results on the 316L stainless steel. And we obtained very good results in a similar work that I will present on the 29th here. And so this is an important feat because technically this framework could be applied to completely different scenarios. For example, here we have done this was a generative task. So this one that I'm presenting right now was a regression one. This is a generative one. So this framework is very, very robust. So as for the future development, prove the efficiency of this framework, we plan to deploy this procedure on the whole datasets to achieve the aforementioned general model. We plan to migrate to a proprietary SQL server because right now we were using one server that's free, but it's free with several limitations. So we want to embed our own SQL server into the library to make it standalone. We want in the future to extend the AI modeling capabilities also to other crystalline structure, because right now it's only composition. It would be nice to extend also to different crystalline structure. And after some polish, we plan to publish the library publicly on GitHub and on PIP. So you can play with it, and I hope you can achieve good results with it too. So thank you for your attention, and if you have some questions.